I made sure that I downloaded the registration of the sessions that were missing on YouTube. So yes, there is only one that will be missing. I don't remember if it's one from normal course one or the lab one, because I forgot clicking on registration. But otherwise, they are there and they are organized. Well, they are associated to the topics as I have been doing for the previous topics. So if you need to access them. Another thing that is missing and that I have to make sure that I put online, I suppose that you prefer, I don't know, I mean, it's a generation issue. I tend to prefer, I don't like videos, and I prefer having the slides. And there are slides missing. So I will make sure that the slides are also there so that you can decide what to use in order to work on the exercises. So that's one thing. The other thing is that I have had some questions regarding the exercises. At some point, I named in Blackboard, you have deliverables and you have evaluation something. And so the other deliverable is, in my understanding, is an assignment. But I think that in Blackboard, it appears like a separate task. The assignments that are to be evaluated are the same, either if they appear as deliverables or as evaluation. I mean, the problem is that I think that I use different descriptions, and so there was confusion. So it's always the same as we have discussed. There are 3 exercises to be handed in. The first one is the MongoDB queries, and particularly, well, the queries were done more or less together, and there is a discussion on Slack about the others. I think that I'm missing to comment one or two, but I'll make sure that I comment them. And so that's one thing. And then a particular thing that was not discussed within the sessions, and that you have to develop and propose solutions, in the indexing part. But well, anyway, that's the Mongo querying exercise. And the second one is the sharding one. And then the third one is the polyglot persistence. Then yesterday, what I did is, since we decided to divide the deadlines, I tried to really have something saying that the polyglot use case is a separate thing. I think that there was some confusion. Only did that one, the polyglot persistence use case. It's only one, and it will be only one, the one that you have to hand in. So I hope there is, this clarifies, I hope, maybe not, but anyway, that's what you have to hand in. Okay, and I also answered Nicole on the on Slack, so that, but I think that you are not the only one, so I decided to do to do the clarification online. Yes, I will try, but I don't promise, because there is quite a lot of administration things to do regarding the management of the course. But at some point, I will try to use some private questions. I will not say who asked them, as frequently as questions, and I will try to put them on the site in a FAQ space, because sometimes the questions that someone asks individually might be useful for the others. So I'll let you know if I manage to do this, so that everyone can profit from the private discussions that I have with some of you. Okay, so said that, I'm going to go further. So in order to finalize the aspects regarding graphs and documents, an important thing to discuss is a comparison between the graphs and the graph solution, the property graph solution, and this is why the document is there, because properties are in fact little documents that are associated to the node and that describe some information regarding the node. And so it is important to compare them in order to know why do we use a graph store, for example, instead of a relational one. Okay? And normally, I mean, it depends on the organization where you work, but you will certainly, maybe you are already very, very young, but you might meet people that are completely used to the relational solution because the relational has been around for a long time now, and because there is investment in organizations regarding the relational solutions. And then at some point, if you see that there is a problem that is better adapted for a graph solution, you have to convince people about the fact that in an organization there will be investment involved in having a graph store solution, and so it is important that you can see the good arguments. And if that is not the case, even for now on, when you will have to address the management of data, it is important that you really see the characteristics, expectations, the kind of queries, etc., the kind of guarantees expected regarding the data you have to manage. And out of this, see the different solutions that are available now and decide the one that best goes to your solution, and even adopt this polyglot solution in order to combine tools and make sure that your data management solution is good, it doesn't create overhead, and really responds to the characteristics of the system that you're implementing. Right, so the way we model graphs in the relational model is thanks to foreign key constraints. And in fact, what happens is that, for example, if you have users, orders, line items, and products, this schema can be expressed as a graph. You have users, you have orders, you have items, and you have products, okay? And in fact, if you see here, this line item is in fact a normalized relation that we need, because we have to make sure that we have at least the three formal norm ensured, okay? And so this little table line item makes this possible. If we had a graph, in fact, what would happen is the line item would be a relationship. And so you would have users, orders, products, and then between order and product, you would have a relationship in terms of a graph, and the relationship would have these properties. Okay. In fact, only quantity, because the order ID would be in the node order, and the product ID would remain here, and the only thing that you would have is a relationship with a label quantity. Okay, that would happen if you model this as graph. But here, since we have to ensure the three formal norm normalization, so we have to have this, and then the connection between the different elements are foreign keys. And then that we have discussed in previous session, the problem with normalization is that it ensures a certain number of guarantees regarding the maintenance of the data in presence of updates. But the problem is the drawback of this is that if you have a lot of queries with joins can become very costly, despite the fact that any relational system has a lot of optimization behind in order to make sure that even if this creates overhead, this shouldn't be seen, or can be transparent to the application. The problem is always the same. When the volume of data becomes huge, then the overhead that at some point was very little, well, it becomes huge. Okay, so that is the pitfall when you have to deal with graphs, representing them in terms of the relational model. Now, in general, when you have highly connected domains, the strategy would be not to use the relational solution. Okay, it is not that easy, because then you have the guarantees. Okay, if you have concurrency, if you have durability, etc., then you have to think about it, because otherwise you have to program. Okay, but anyway, let's consider that the expected guarantees are not very important. So if you have a connected domain, it's sure that the relational model will have problems. And well, the example here, even in this little part of a schema, if you have people and you want to represent my friends, you see this becomes a little bit obscure in the relational model, since we cannot point into tuples that to themselves, and so we have to create this separate a table in order to represent this. So first thing, there is the challenge of making it possible to represent connected domains with relations. Okay, so that's the first thing. And then the second thing, what happens if we want to know who are Bob's friends? In SQL, the solution looks like this. This is SQL3. So you have the operator join in the as first citizen. So what happens is that we are going to select persons. So from the relation person, and then we are going to join that with a person friend, so the second relation, such that the IDs are the same. So that's a normal join. But we need another join in order to ensure the transitivity expression, where you join that with Bob. Okay, and in that way you have the friends of Bob. So no one that has a good level of knowledge in SQL would be surprised, or this, for example, if you apply to any position, if you go and see Glassdoor questions about the relational, this is obvious that someone with fundamental knowledge is able to express. So expression, let's say that it's not an issue, but as we say, the problem is what happens at execution time. And so now, if we go further, before we go into execution time, what do we do if we query Alice's friends of friends? So a level further. So how do you say that? Imbriqué. Sorry? Embedding, yes. I have a person here. So the embedded composition of joins becomes much more complex. And as you add levels, imagine that we want to see at the 6th level the friends of Alice, then you have an embedding of joins that, again, no one is scared about expressing that in SQL, but the expression becomes kind of weird, you know? And particularly because of this, because you have to make sure that you avoid pointing to a person with the same person, otherwise it becomes costly. So computationally complex, and queries extend to 4, 5, or 6 degrees of frames, deteriorate significantly due to recursive joins. The problem is recursivity. And I'm sure that you remember not last session, but the session before, we saw that in Cypher it is very simple to solve it, to express this, well, to solve it, no, but to express this, yes, because you have the clean operator within the expression of the queries. And now what happens with performance? In fact, what happens is people, when they started to propose graph data stores are possible solutions for dealing with this kind of data, they did an experiment. And what they did is they used more or less 1K people, and with average of 15 friends per person. And the path exists is looking for friends. Okay, so whether I can traversing my connections, whether I can reach a person. Okay, so that's a classic expression of traversals in graphs. So the idea was to implement this path exists between A and B, limited to depth 3. And the idea was that, well, they executed it in the relational solution for these 1K people. It took 2K milliseconds to the path exists to be executed. And an important thing, I suppose that you know this from your relational courses, between the server and the client that asks queries, there is a cache where, in fact, going back to the iterator model, the system gets data, caches them, and then starts providing you with a result. And the idea is that in order to ensure performance, some of the results of queries remain on cache. So the system, out of statistics, knows whether the queries are very recurrent. And so in order to ensure performance, the partial results remain on cache until there is an update, and then you have to play with the cache. But when there are a lot of readings, so the cache is a very important thing because it eliminates disk I. Okay, so well, that's a function of the cache, but relational systems rely on cache management in order to ensure performance. And in this case, the cache was implicated, okay, because there are other experiments when the cache is blocked in order to see really other performance issues, but in this case it was there. Now the same thing was done with Neo4j, and it took 2 milliseconds, okay, to the same query to be executed, and again using the cache. Almost any store uses a cache. And then when they increased the number of of people to be to be explored, and so the graph in fact increased, and it remained into 2 milliseconds. Okay, so this to say that given the backend data structures used in Neo4j that avoid this normalization, it is possible to have much better performance because the data structure is conceived for this type of queries. Okay, and this is why queries are an important criterion to guide the choice of your of the data store that you should use. Okay, you have queries, you have the data characteristics, and there normally you can choose the right model, and so in consequence the right store to be used, and then comes the guarantees, and with that, out of once you identify the family of stores that you need, then with respect to the guarantees, you have to go and see within this family which are those that best ensure the guarantees, non-functional guarantees that you are seeking for. And so that would be a kind of vademecum of what should be done in order to make this type of decision. Now, with respect to performance, since we promised from the beginning of the study of NoSQL that we were seeking for performance, so of course, performance will be for simple data management requirements much more better than relational databases. Okay, things change when the guarantees become a very important issue. Then NoSQL guarantees the performance of relational solutions. So anyway, when there is a huge connection, join intensive query performance, good candidates to be used are graph databases, and particularly also when you expect huge growth of the database size. Now, of course, well, I don't know how, now that you have seen, well, you know SQL and you have seen Cypher, I don't know with which you would feel more comfortable. There is also the problem of the curve of learning that is there, and the expressivity of the languages, and how you can embed other operations in your queries. But anyway, these are important things to consider. So until here, it's criteria to be chosen in order to decide whether to use a graph data store solution with respect to a relational data management solution. Okay, so that's what we can say until now with respect to graphs versus relations. And then, as I said, documents are there because the properties work as documents, and there are some graph stores that really combine both. Okay, so you explicitly deal with documents and deal with graphs. Do you have questions until here? I see, well, I think that the chat is just previous discussion. So do you have questions until here? Right, everything fine? You will buy Neo4j now and use it in your projects. Well, I think that a nice exercise here, we are not going to build a complete project because of the type of expectations that the program specifies. I cannot ask you to provide a complete project like the ones you normally do in databases or something like that. But if eventually you have projects related with social networks, etc., try to use Neo4j or some other one and see how you manage to deal with your projects. And that would be a nice exercise to be done. Okay, so more on graphs. In fact, as you remember that we learn when we learn relational model, we learn that there are 5 um, basic operators related to the relational model. Which are these operators? Give me one. A graph. Well, it depends on what you have, on what you want to do. If you are exploring the connections, so really the network, then a graph would be a good solution. If not, then you have to think. If you are dealing, for example, with the timeline of your Facebook account, then I would say that a document database would do the job good. Or if you are just managing like the agenda, so the people that you have in your friends, but um, without interesting yourself in how they are connected with each other and how, then a relational solution would be great. In the MyNet project, this is what happens. So for dealing with the the address, the languages you have, etc., a relational solution is very good, because there you it's easy and structured, completely structured data. No? And then for the timeline is an interesting thing to do, because there, well, you have the posts that are little documents, and then you can have, sometimes you have the geo or the temporal tag, others not, etc. So documents would be maybe a good option, and then you have also the retweets, which are posts themselves. If you start dealing with the retweets there, you have to see. I would say that a document, but I would be ready to discuss another alternative. And then for the social network, so the network itself, of course, a graph is an well adapted data structure in order to deal with that. Because I mean, the functioning of the social network is that is it. You have your network. It proposes you new possible new connections, etc. So it controls the flooding of your comments or of your information, depending on a depth of connections in your network. So there are a lot of operations that concern the network itself. So that's yes, that would be a kind of immediate reasoning to reconsider. You're welcome, David. Okay, so what about the 5 operators in the relational model? Which are them?
Teacher, I don't remember a lot, but it doesn't have to be related. It is related to acid or not?
No, the five operators of the relational algebra.
Ah, okay,
Well,
okay.
we have projection. Uh-huh. Projection is one. The other, union, yes. The third, selection, yes. We need two more. Cartesian product and difference, yes. Okay, so these are the five. As in the relational, and this is something that you really have to keep forever and ever, okay? Again, this is a glass door question. No one can forget this. So once you have this, when you move to another data management solution, you have to look for that, which are the operators that are associated to the data structure or the data structures that are the core of the store, okay? So when we are in graphs, there are several operators. Of course, the general family of operations is traversals that normally is instantiated to the notion of path. We are looking for paths within the graph, and that's something that you learn, I suppose, in discrete maths or in something like, or in data structures, I don't know, things like that. Okay, so graph operators are community detection. We want to look for subgraphs that can be considered a community. That, since we are users of the social network, we have a lot of examples. The community of users that compose the contacts on Facebook, if you still use Facebook, that compose your family, that compose your acquaintances, that compose people that are interested in French cinema. Okay, so this operation of looking for communities within the graph is an official operation on graphs. Okay. And then, as in the relational model, that's another thing that you have to bear in mind and master as your name is the different implementations of the operators, particularly the five ones. Again, a glass door question is being able to identify the type of joins that can be associated to the relational model and the classic implementations of the joins okay, with buckets, without buckets, etc. So that's a Glassdoor question. If you want to have a nice job instead of tagging web pages, then go for it and study that. Okay, so as in the relational arena, in graphs, community detection can be implemented with many different algorithms. For the time being, as I said, we are not going to go through the algorithms, but when we will start doing analytics, we will study the most common ones like label propagation, Louvain, etc. So these are again those that come normally into the discussion when people say that they have managed graphs. Second is centrality. The one that, I mean, centrality is often explained through PageRank because Google and its competitors have been around for quite a long time. No, I suppose that again in information retrieval, you know, you studied the principle. Normally, what happens is that given a page, you are going to count the number of other pages that point to that page in entry and I mean entering and pointing out, and then out of these, you are going to suppose that if there are a lot of sites pointing towards that page, that page will be popular, okay? And you can rank the pages with respect to their popularity. And that is also there on Facebook, on Instagram, etc. So we have influencers and influencer. What is an influencer in the social network? It is a user towards whom a lot of other users of the network point to. Okay. So the general operation regarding graphs based on which PageRank works is called centrality. And again, there are many different implementations to centrality. Then similarity, nearest neighbors, for example. So that's the third one. The fourth one is finding paths and searches. So that's the real traversal. Okay, is there something that connects? I don't know, Sting with me. Okay, so that's one. Or Michael Carey with me. You all know who Michael Carey is, of course. And then, okay. So, and Barbara Liskov, do you know who she is? Barbara Liskov is one of the Turing Awards, one of the few women that have had a Turing Award, and she proposed the object model. So the one that we all use was proposed by her, and she obtained for her work on that the Turing Award. Okay, so going back, pathfinding is the thing that we have to know about graphs and searching within graphs. There you find all the applied mathematics world, just for that problem, and it is one of the basic operations of graphs, on graphs. And then there are two supplementary ones. One is predicting links. How do we know that a graph is complete with respect to the mini world that it represents? We never know. Okay. The principle is that we try to do as much as possible, but behind we know that we might have missed relations between the nodes because nobody specified them, because they are hidden within the knowledge of the data collection, and we do not know them, okay? So a very interesting thing to do is whether we can predict that two nodes can be connected in some way. And that, again, is something that social networks do a lot. They propose, since the problem is difficult, what they do is they look to our properties, into the data regarding our behavior in the network. And then they look similar behaviors on other users. And then they tell us, are you interested in this? Is this a person that you might know? Okay, and therefore they, if we say yes, what happens is that we do a positive reward to the algorithm. And so it will try out of that to predict new ones. Okay, so it's like when we say yes or no, we are training an algorithm, and so that the next time it will be able to find possible new links for us or new information that might be interested for us. And that's link prediction. And then there's pattern discovery. So link prediction is simple because it's one-to-one. Then what happens for subgraphs is this community close to another community of nodes. Okay, so that's pattern description. Or are these people complotists? Okay, so is there a pattern on their behavior within the social network that tells us that they are um, addicted to complot? Okay, so these are I mean, I give examples like that in order to tell you that it's not again in the ivory tower for mathematicians and etc. people that never touch the earth. The earth is there behind the algorithms, and it's looking for them. Now, out of these, there are plenty of graph stores. We have studied one, but there are a lot, and they are still emerging because we have seen that, I mean, we, the community, has seen that graphs are a promising, very promising solution in order to understand complex systems. Okay, so we are surrounded of complex systems. We are ourselves, we are a complex system. The social society is a complex system. The climate is a complex system. So anything almost that exists on Earth is a complex system, and we have discovered that graphs are a good way of representing them and understanding them, predicting their behavior, and eventually reproducing their behavior. And this is why a lot of graph solutions emerge. So another, for example, that if you are really interested in having a look at graphs, Arango, for example, is another very interesting example. Cosmos DB, again, another very important. Titan is also very important. From among others. Okay, so anyway, this is the list of popular graph stores, and even if you haven't studied them, it is important that on your general culture, you are acquainted to these names, okay, these products. Then that's the stores. And then regarding particularly operations, there are other proprietary solutions that are normally related to deal with a particular operation. Okay, since operations in graphs are very complex, sometimes what communities do is they focus on one operation and they try to dig into the matter in order to provide the best libraries possible, for example, in order to deal with that operations. And so that's one thing. And the other thing is that the database community is not the only one that has been interested in graphs. At the beginning of the introduction to graphs, I named linked and semantic web. Okay, so that community came up with well, they addressed the problem as a knowledge representation problem. Okay, and out of that, they came up with RDF, which is a graph-like representation that is used in order to represent content on the web. And so there is a huge community dealing with RDF, and sometimes it communicates with graph stores, but there the problem is not a problem of guarantees of querying, or even if there is a querying language, but it's more representing knowledge. So I suppose that knowledge representation you have addressed in artificial intelligence. One of the questions of artificial intelligence is exactly that. How do we represent knowledge? You know, of course, the name of Minsky. Minsky, no Minsky like it's written there, Minsky. Like that, Minsky. Do you know the name? No, okay. Minsky is considered one of the fathers of artificial intelligence. Again, nobody can live alive without knowing Minsky. So, prominent person, knowledge discovery person, And he was the first. In fact, the relational model. There was what we know now as the artificial intelligence community that knew that knowledge representation was an issue. And since computers were there, the question was how do we best represent knowledge from the mini world so that we can use computers in order to explore, to automatize processes, etc., to analyze, to deal with data, okay? And it was a huge question because data structures were at the beginning of the story, etc. And so Minsky had an institute, and he came up with something that looks like it's between the relational model, but with, it's entities connected among each other, like the grandmother of, or the grandmother of entity relation. You see this kind of solution. And so Minsky came up with this, and so again, Google him within one of your idle moments and have a look on what he did. And in Mexico, there was a very reputed scientist that passed away 1 or 2 years ago, and he was a student of Minsky. And he was one of the fathers of robotics in Mexico. Jose, I'm coming back with the name. At some point, he went to the lab for a keynote. Okay, so back to the matter. Since I say that there are people just focusing in addressing one question or one aspect of dealing with graphs, in fact, there is another family that today is connected with stores, okay? So this is why I address it here, is a family that develops analytics tools on graphs. In that principle, instead of having cipher or a declarative, more or less declarative language, what they say is, let's program and provide built-in methods and operations within libraries so that people can deal easily with graphs, but without expressing queries. Okay? It's more like step analytics, processing approach. And so there are libraries in Python, and one of the famous one that we are going to compare against Neo4j is NetworkX. There is again that we will see in the data analytics topic. Spark graphics is another one. There are a lot of deep learning models. I suppose again that deep learning, you touched a word in artificial intelligence. So artificial intelligence is smoothly being connected with the data management, etc., because we want to do analytics. And so deep learning models deal with graphs, and particularly in order to do classification, link prediction, graph clustering. People have come up with deep learning models that seem to be interesting in some situations in order to perform this kind of operations. And so there are libraries only offering these kind of solutions. And then there are graph processing systems. Normally they work on parallel settings like Giraffe from Apache and Pregel. And so again, they provide a lot of already implemented algorithms in order to deal with graphs, and particularly in parallel settings. And so they're all communicated. I hope to have time and show you how to connect, in fact, this famous Spark with Neo4j in order to do the link prediction, for example. So we are really making them interact among each other, because we have performance issues to address, and then also performance in the sense of having precise answers to queries where we touch the analytics part and not the direct aggregation or classic querying of facts. Okay, so that's, you see, the perspective, or I mean the landscape of what is graph, behind graph systems and graph stores. As I said yesterday, I mean, you could have one or two courses only devoted to this kind of solutions. Here we are just touching them because we are interested in cloud computing and in big data, but this is part of a huge content that could be studied separately. What is next? Oh, yes. So until here, do we have questions? I'm going to have a little coffee because I've been talking a lot. So do we have questions? All clear? Good. So, yes, please, Mauricio.
Just to say about analytics. So I use that. I'm still do not understand what are. So the use of this
What is
analytics.
analytics? Do you mean that's a question?
Yes. What is the purpose of the analytics?
Analytics, okay. Analytics is those questions that cannot be answered with classic querying operators, like computing, like selecting, like projecting attributes, like doing aggregations. All these operations are related to the data structure of the data, and then to the explicit content of a database. Okay, how many employees do we have? How many users does Facebook have? How many people are connected to my social network? Okay, so this name people that live close to my home or close to my work. Okay, so this kind of queries are queries that explore the content, the immediate content of the database, and provide you either with aggregative results or with tuples or elements that are contained in the database. And then analytics is you are going to try to discover information or knowledge hidden behind the data collection. Example of this, out of your behavior on the queries that you ask on Google, can I figure out which topics are you interested in? Or can I figure out which is your major, your professional major? Can I figure out how old are you? What is your nationality? Okay, if it is not explicitly stored in the database. Okay, so this kind of discovery of knowledge behind the data is analytics. And in fact, there are two big families for doing analytics. The first one is classification. Okay? Can you define a community within your social network? Can you define a community within the different variants of the virus SARS-CoV-2? Can we observe the preferred color for Mexican people living in the States? Okay, so this is classification. And then there is another family, which is prediction. Prediction is prediction. So I want, out of the observation that I have made, or out of a set of data that I have collected, is it possible for me to predict your next purchase on Amazon? Or what is the next page that you are going to load on your browser? Should I cache it, put it on cache, or not? For example, I want to provide browser with very good performance. So out of the behavior of everyday's access to pages, I am going to try as a browser to prefetch the pages that you look for, such that when you click, the page is already cached and you have the result almost immediately. So this kind of questions, of queries, you cannot answer with classic data as operators related to the data structure or the content of the data, and there you need to analyze and perform other operations.
Oh, okay. Yes, I understand now.
Good.
Yes, all good.
Good. So, for example, in big data, many people associate big data processing with that. You see, suddenly they see a lot of data, so they think lots of data, lots of hidden knowledge behind, so let's go and exploit the data so in order to acquire knowledge. Okay, and this is why people have a kind of immediate understanding of big data related to analytics. Which is not the same. Big data is much more than that. As we have seen, there is storage, there is management, there is a lot of backend things that we as computing engineers should be interested in and operational. But then, as I said, the second topic of the course is going through those matters and see how do we put in practice these operations and operators in the cloud, and how do we choose them, etc. More questions? Fine. So there are two aspects that we have to discuss regarding, in general, NoSQL stores. So now we have seen at least two examples, classic one, documents, and then a more funky one, the graphs, and knowing that there is columns, etc., that we don't have time to touch. But anyway, we have seen the overview of NoSQL stores. And an important thing that we have to zoom into is how it's managed by these NoSQL approaches. And so the question that any NoSQL, any data management system, being SQL or NoSQL, has to think about, and us as engineers, if we want to provide a data management solution, we have to think whether storage will be only on disk or not. Okay. So as we all know, the best way to achieve performance for managing data is making sure that data is on RAM, okay? Because in processes, RAM is related, is connected with, I mean, piece of RAM is in the same space of a process, and so the access is direct. Okay. The problem with RAM is that even if we have cloud solutions, we never have enough RAM to deal with all the data that might be required by a process, because there is the process. If you think about the process querying data, there is the data coming from storage support, and then there is the data produced within the process, and all this has to fit into the RAM, and this is not possible, physically not possible. But anyway, NoSQL systems, we studied that when we first started to profile them, is that since they are looking for performance, they are going to try as much as possible to lay data on RAM. As said in the slide, yet this is not always possible or desirable. Okay, so the question is that these kind of systems or any kind of data management system has to make decisions on how to move, which is a strategy, or which are the strategies to be implemented in order to move data from RAM to disk. This operation is called eviction. Okay, so that's the jargon of the discipline, and so normally this is automatically configured by the system. But if you are advanced use of the system, you can modify and adjust eviction strategies depending on your requirements, okay, on the applications running on top of the system and of your requirements. So the normally NoSQL and even SQL solutions deal with buckets of data. Okay, so the idea is when you are going to evict a bucket into disk or not. Okay, at which moment do you evict or not the data from RAM so that new data can come? Normally on disk, NoSQL servers deal with key value pairs. Okay, and so persistency is done or is executed by loading data, closing and reinitializing it without having to load data from another source. Okay, so you have different sources, and what happens is that within one source you put down and up the data that you are managing in that source. There are hot backups, which means that loaded data are stored on disk so that it can be reinitialized in case of failures. Okay, the problem is that you want to go fast, you are seeking for performance, but you do not want to lose data. And as we all know, no system is free of failures. There are always failures, and in case of failures, you do not want to lose your data. So the strategy of having hot backups is that you are going to back up the data lying in a disk into other disks, so that if there is a failure, you have the data available. And the question is, how are you going to organize these hot backups? Okay, so you as an engineer have to make decisions on how to do it. And then with respect to storage on disk, the disk is used when the quantity of data is higher than the physical size of the RAM, obvious. Frequently used information is maintained in RAM and the rest is stored on disk. Okay, so the question here is, how do you know what is frequently used information? Well, as you all know, as in the relational solutions, there are statistics. So the system maintains statistics, and normally if you're an administrator of the DBMS, you have to look into the statistics in order to tune your system and decide, for example, which are the best protocols in order to do hot backups, make data persistent, and then decide when you are at which moment you are going to evict the data from RAM. Okay, so this is a great computing thing. Okay, so if you really like computing engineering, this is what matters. Okay, so imagining building a data management system and having to make sure that all these solutions are there and working together such that the system can manage the data with specific guarantees. Okay, so if this is, I mean, this is what is interesting. Nothing is more interesting than being able to develop such a system. Okay, the other things, I mean, anyone can do. Okay, so there should be then strategies that should ensure each node. So we are thinking of a cluster. Okay, so we have several nodes in our cluster. So each node will maintain RAM information as I said, in key value pairs. And the problem is that some keys may not be found, or they can be stored in memory on disk or on disk. Okay, so the problem of maintaining the keys is a problem that someone that builds a data management system must deal with, particularly when you are in a cluster, because what is key in a cluster loses significance in another. I think that you have seen in distributed systems. This is why we cannot use pointers, and this is what we use normally serialization in order to deal with complex data structures, because pointers lose their significance if they move to another context. So this is the same. You have key value pairs, but what is key in one node, it might lose its reference in another node. So that's a thing to do. And then the process of moving from information from RAM to disk should be asynchronous. So the challenge, I mean, you're not going to stop everyone and say, wait a minute, I'm going to do a backup, or I'm going to evict some data. Stop the execution now. Things go on, processes continue, and asynchronously, you have to do this process. And so there are queues requesting the disk. Okay, so the disk is not something that is there and that anyone can access. It is controlled by a little software that deals with these queues, and so the queues and the execution of the operations must ensure that no information is lost while you are waiting, and then a failure comes, and then whoop, out. No. So you have to deal with that, and then put into disk and make sure that the disk does not overflow, because otherwise you have to go back and forth. That is something that you saw in sharding. You know, when you have the shards, and then at some point one element is moved to another. So this is part of the solution that we are referring here. So, and this depends in periods with a lot of writing requests. So clients can be notified that the service is temporarily out of memory unit because information is being evicted. So that is very bad. The idea is that you avoid this. Okay, so you keep accepting write operations, and you queue them, and you do some strategy so that for the applications or the processes, this is transparent, but behind the system is doing a lot of operations in order to make sure that everything goes smoothly. So those are the key elements that, well, we are, of course, again, we do not have time to go into the deep matter, but these are elements that are important to consider for you as computing engineers. Okay, so understand what are the implications behind of having solution A or B, and what you are going to look for. Okay, so what is the strategy implemented by this system when eviction is needed, when duplication is required? How are hot backups performed within solution A or B? Okay, so that's what you have to bear in mind with respect to this. So I'm going to stop here. We still have to discuss about memcache and locking. I will do that in the next session, and very briefly, so that we can move to other topics. Do I have questions until here? Good. So if you are, for example, looking for internships and that, try to look for internships when you have to do these kind of things. Anyone can do final systems. This is normal, but touching these kind of things is what goes to the second level of engineering. So These are very exciting things to do. I think that I saw yesterday an announcement. I don't know what does it mean to have a Google desk. I don't know if they are selling Google solutions or if they are really talking about internships or something. But there's possibility to have internships in Google and in Microsoft, etc. I have had students from MUTLAB that are working there. So there is people that know the university and that can be receptive to applications of internships. They're very competitive. It is possible to ask for them, and I believe that this can be a very nice experience. Either that or going to a research lab. There are today a lot of research labs that have startups aside. For example, TU Berlin has a very strong database group. They are working with Data Bloom, for example, which is a startup, and also Saiwan, which is another startup related to TU Berlin. And the group is really strong. If then now we haven't seen the data analytics, but the Qatar research center in Qatar is very strong in data analytics. Barcelona, for example, I have worked in the Barcelona Supercomputing Center. There are huge groups there dealing with very interesting projects, and they have collaborations with Mexico. So these are kind of things that if I was young, I would go and look for, because this, as I say, this provides you with extra know-how and extra experience out of the undergraduate experience. Anyway, okay, so I'll see you on Tuesday for practical activities. And meanwhile, I remain available on Slack if you have questions. And I will make sure that all the slides, etc., are available so that I do not block the development of your exercises. And if you don't have further questions, we can close the session here. See, you have a nice Saturday. Enjoy your weekend.
Thank you, doctor. You too.
Ciao, ciao.
Thank you, doctor. Have a nice weekend.
Have a nice weekend. Work hard. Google Minsky.